theoretical study today. My presentation title is there any mobile phone? A numerically worst case no tilted holes effect on overall thermal resistance for a masonry brick. Here we have a conventional masonry brick, 33.5 centimeter thick. It has very common usage in Turkey. So to propose an alternative masonry brick configuration to increase overall thermal resistance. Doing this by preserving the following for the existing and the proposed bricks. First of all, the solid to air ratio will kept constant. The weight also will be constant for both configurations. And space to leave, of course, for the wall will, as a result, will be same for both applications. Here is the theory behind this problem. As we see, first cavity is very well-known configuration, square cavity flow, natural convection flow. If we turn the square to 45 degree, left or right, you will get a new configuration, but the gravitation, of course, remains the same. So the balance force will be work the same. As we see, the first configuration known as balance induced wall configuration is the walls parallel to gravitation direction, and the second configuration we have a balance opposed configuration, so the upgoing air will face inclined surface, so the circulation zone may become smaller than the original one. So at the corners, we may expect a weaker or almost stationary regions. These considerations is the main motivation for us to perform such a study. I'm going to, I cannot read this. As we know, the basic mechanism within the house is natural convection. We also know it's very sensitive to the boundary condition as well as the geometrical configuration. A balance opposed wall configuration is considered to reduce this level of natural convection and resulting in increasing thermal resistance. The main purpose, of course, for a wall material structure is to increase the thermal resistance. Here, this is actually, the corresponds to this conventional masonry brick configuration. We didn't change the whole brick, but we modified the holes, of course, theoretically. As you see, these are regular size, and this is a little theory, well-known governing equations for 2D state-state natural convection with Bose-Nassier approximation. We use Fluent software to get result. I am going to present the results of this numerical work. Here, if we, this vertical horizontal wall indication shows the conventional brick holes, and the inclined walls, it's proposed brick holes. So here we see visible, or let's say noticeable amount of increment in thermal resistance. Of course, thermal resistance is going to decrease with increasing thermal temperature differences in nature. The increment rate is of course the same, but inclined walls shows very good performance in terms of thermal resistance as we expect. Here we change the thermal conductivity of material. So we see important differences between the material. This, I think, corresponds to some concrete and soil material. If we go further for outputs, for fluent produced results, I will show a magnified, exaggerated form of this picture. We cannot see details. This is for inclined holes. If we go further, yes, here we have, here is, this is what we expect. This is well-known, conventional, a classical result of square cavity flow. Here we got the new one, a proposed one, and here the intensity perpendicular isotherms and top and bottom of the hole indicates the reduction in heat transfer, which almost insulated, in this section of the hole. So we can also, this is typical holes. The other holes also behaves similar. Okay, I will come back here. We have a percentage increment in we also include thermal radiation. Surprisingly, taking into account thermal radiation reduces the increment in percentage, as we see. Increment in percentage about, about 11 to 14 or 11 to 15 reduces to 6 to 9. If you go further on the results, okay, we can conclude this work as, I will turn this aside. We know in the literature, attempts on the thermal performance improvement are mainly focused on reduction of thermal resistance. In this present work, a geometrical configuration without altering the overall solid area ratio is considered. The main conclusion of this effort as we saw just resulting graphics, the observed thermal resistance in removed is about 11 to 15 for the fully convection assumption case. Only 6 to 9 improvement for the radiation exchange included case is observed. As every numerical study, here we need to confirm these numerical results. So because of that, we apparently produced a 3D printer masonic brick examples here. It is under experimental study. I think you will get the result in a few months. So after that, I think we will say something more precisely. And thank you for listening to me. If I have any question, I can take it.
Thank you very much for this presentation and good timing. Questions? Do we have some questions from the audience? Livio?
Very interesting example how a simple idea can improve without any extra cost in producing the brick in that case. And not surprising that with radiation is coming to be lower the effect because it's a parallel mechanism. I'm interested to know what kind of thermal conductivity you are going to have in your experience using 3D printer material, because it can be quite different from what you have in reality.
Yeah. As I showed the last 3D printing, I think what they call it filament. It's actually I don't have the number, but it is available. I don't have the conductivity of the material in my mind. You know, it is, we know it.
Yes, because
it's a kind of what they call it, filament. Or
I'm saying.
Plastic based. Because it is easy to.
The plastic material, which is a bad conductor, that could be in the right range or not. The point is, as you showed before, that the effect depends strongly on the thermal conductivity of the material. If you have two very high thermal conductive material, then the effect is very important because convection is dominant. But if you have very insulating material, then you cannot see anything probably by your experience. This is the risk. You have to check the right thermal conductivity in the range of what we really have as building material. This is the point. My suggestion is just build up a brick as a brick by hand. It's not so large a problem, but then you have the right material for your experience.
You're right, but if I think we need to go back to fluent software to use that conductivity and to get the same conductivity to compare. But as you said, it is true way to build that model with a real material.
It's not a problem.
Yes.
Thank you.
I understand what your point.
Thank you.
It's a great pleasure to share our research on a mathematical model for determining the optimum building height in urban development. And we know that the building stock will be expanding. And in parallel with this, also the available roof area that is available on buildings will be increasing. But how true is this? If we question these values, for example, we see that the number of buildings is increasing, but the height of the buildings is increasing faster. So as the building stock is increasing and the area, available roof area, expected roof area on buildings is projected, how true is this? This was one of the founding motivations of the research work, because as we see in this example, the high-rise building is a high-rise building, but the rooftop area is like the tip of an iceberg. There is little rooftop area, if any. So when we are looking into urban development and questioning ourselves, would we prefer high-rise or low-rise development? This is also important from the available rooftop PV and the building integrated photovoltaic applications that we may be targeting for. In a low-rise building, on example, there's relatively plenty roof area, there can be, and if we consider that also the rooftop area is used not only for electricity generation, but also PV and solar collector integrated PVT, or as in our research, we're also proposing photovoltaic thermal and cooling. It's a new type of solar brick. If these are integrated, then we may even be in a more favorable term with regards to the load share that is available for the building to provide for its own energy from solar energy. This is what we call the load share ratio. It's a ratio of the irradiance, the solar area for this photovoltaic, and the efficiency of the photovoltaic panel, and the diversity factor. Diversity factor also depends on the number, the height of the building area. So what we try to do is we try to question ourselves when we're targeting the number of floors or the height of a building, when this is increasing, what we must also realize is that the possible self-sufficiency rate that the building is able to provide for its energy needs from solar photovoltaics is also decreasing. So another aspect was if these architectural designs are not optimizing the shading effect and also the solar gains, the cooling loads might also be increasing. So this is another factor. Another factor is the operating energy for HVAC lighting equipment and also vertical transport is much higher in higher buildings than in lower buildings. When we try to look at this conflict and this dilemma, we see that in vertical developments, yes, there can be advantages. For example, urban infrastructure costs can be lower. Also, transport costs can be lower because there are less transport distances in the city, and there can be compact urban form. But on the other hand, horizontal development can also have its benefits, such as solar shading effect in buildings is lower. One building is not affecting the neighboring buildings to the same effect. And also the embodied energy and exergy can be lower. And so there are different trade-offs between vertical and horizontal development. And in the algorithm that is developed, there are different variables to consider for these trade-offs. And we also applied this to a pilot area near Ankara, which is the capital, in Polatlı. This building area is expected to have about 200,000 inhabitants. And the planning was integrated into two cases. The first case is a conventional district heating area based on natural gas, and the second one is using renewables, mostly solar, for a hydrogen city. And we tried to provide guidance for the urban development. Also, two options were considered. One was integrating a glass facade on the buildings, and the other one was normal conventional building materials, but also using the innovative solar brick with photovoltaic thermal and cooling. Here we see that as the number of floors are increasing, the embodied energy is also increasing for the structures, the building, and particularly for aluminum buildings. This is one of the materials that has one of the highest embodied energy and also embodied exergy, as is summarized in this table. And in the algorithm, there are different variables for the embodied energy, but all of them are indexed to the CO2 emissions responsibility. So what is needed for urban planners is when they look into an area, we must also think about how the embodied energy, the embodied exergy, and how these are going to impact the CO2 emissions responsibility. So there are some constraints. We want to find the optimum linked for the district energy system, and also we want to reduce the power demand. And where we're locating the sub-stations, these are all optimized. And with all this optimization, we can also arrive at the total area that is required to satisfy this population of 200,000 inhabitants. For the CO2 emissions responsibility, this is also indexed to the racial exergy management efficiency, how the energy resources are allocated in that area. And with all of this, I would like to share the results for case 1, which was our conventional district energy with natural gas. And we see that when we are looking at the avoidable CO2 emissions, this is much higher than in the other case. And 10 floors is the maximum building height. This is for the conventional district energy system. And yes, here we see the 10 average number of floors with different diversity factors provided parametrically here. And this is for the other cases, for the solar brick option 2. And in the second case, for the hydrogen economy model, our CO2 responsibility based on the racial exergy management efficiency is lowered. And we also see that the maximum building height can be a little bit higher. It is not 10 floors anymore, but it is 25 floors that we can accommodate. But as you can realize, it's not 75 or 100, so there is still a limitation that we must impose, because as the building height increases, the load share ratio is affected unfavorably. And for example, here, the optimum point that we're able to reach with the different diversity factors, it is changing with the average number of floors. And when we look at the minimum point for the CO2 emissions, we see that it is, has a dip there. And for the case, it's at 25 floors. So when we're looking into how we should design future cities, planning for area, planning for the load sharing factor, planning for the average number of floors in a building will be instrumental. Here we see the hydrogen economy model in integrating a multitude of renewable energy sources, biogas, wind, solar, and geothermal. And we also see here that the heat from one system can be made into an input to the heat necessity of another system. For example, the heat of the PVT can be used in as partial heating required in the anaerobic digestion process to support that. And what we want to do is we want to increase the use of exergy as much as possible, particularly in not only PV, but also PVT and PVT with cooling. In this sense, in this respect, we want to say that for urban planning should be based on maximizing also the rationality of allocating the energy resource to that area. It's not only an urban planning issue, it's an urban energy planning issue. And according to the International Energy Agency, cities currently use 365 exajoules of energy. And this corresponds to about 60 to 70% of all the primary energy usage of our world. And if this is going to be increased in a 2-degree scenario or a 1.5-degree scenario as implemented for the Paris Agreement, then we might find ways to also integrate urban planning and urban energy planning into these aspects. So when we compare these two cases, we see that the second case is more beneficial than the other one. So in conclusion, one lesson that we would like to give, the message is urban planning is very much dependent on the number of floors in a building. And when we're targeting net zero buildings, maybe we should also target net zero energy and net zero exergy communities and districts. And in so doing, then we can truly reach sustainable urban development. And I think that the theme of this conference for climate proper built environments and HVAC systems is very well fitting to the challenge of reducing our energy usage in urban settlements and urban areas. Thank you very much for your kind attention. Değerli ilginiz için çok teşekkür ederiz.
Sevgili Şiir Kılkış'a çok teşekkür ediyoruz. Thank you very much for this valuable presentation. Of course, we have to look at the problem at urban scale, not only single building scale. It is important, so in that case, it is easier to solve the problems. It is easier to integrate in a feasible way, integrate the renewable energy systems. So thank you very much for this presentation. Maybe one or maximum two questions we can get, or save your questions. Okay. One question.
Quite interesting. One question that came to my mind is, okay, if you have many buildings with similar sizes, we have also the effect of shadowing.
Yes.
So did you take it into account, the shadowing effect of
Yes.
some buildings in the others?
Yes, currently these are integrated into the mathematical model on a parametric basis, but we are actively using also software programs to model this area. So in the upcoming stages, these may not be parametric anymore, but they will be built on the urban planning results.
Okay. Thank you very much. So we have to skip to the last presentation.
Everybody, thank you very much, Professor Yılmaz, for presentation. Before starting my presentation, I have to thank to Professor Arsoy and Professor Çakan and organizing committee to perform this wonderful event. And today I would like to share my study about site selection for cogeneration systems in urban areas and modeling of dispersion of emissions among the buildings. There are many presentations now. Professor Kılkış mentioned it, and in the previous session, Kılıç, I'm sorry, I didn't remember if it's wrong, mentioned PM10 emissions. And all of them are important topics, and that we have to think about it. If we look, or if we start with the global warming case, as you can see, greenhouse gases increases in the atmosphere. But also, the urban population and rural population has a trend as shown in the slide. And as you can see, for the projection of 2050, rural population or urban population will be doubled to rural population. And of course, the carbon dioxide emissions, if you look at the carbon dioxide emissions of the sectors, electricity generation and heating has great share when you compare the other carbon dioxide emissions of the sectors. There are many carbon dioxide projections and studies, what will happen in the future. And as you can see, if we don't take the measures, our world is getting warmer and warmer. And maybe the most efficient way to generate electricity and heat and simultaneously cooling, which means that regeneration system, is going to be the most efficient system for now. And but we don't consider about the emissions and how these emissions are removed, and especially if you think to install these regeneration systems among the buildings, especially high-rise buildings. With the enactment of energy efficiency law in 2007, cogeneration systems were included in the scope of the support. In addition, the energy performance regulations of buildings in 2008 stated that it is necessary to investigate the possibility of production from cogeneration and renewable energy sources and the feasibility of economic feasibility in buildings and usage of more than 1,000 per square meter. Article 23 of this regulation stipulates that if the total construction site is at least 20,000 square meter and the system cost doesn't exceed 10% of the construction cost, that should be applied. But the distribution of emissions from these installations, which are usually located in urban areas, is not considered. I'm not sure how about other countries in European Union or world, but for the Turkish legislation, we don't have an agreement for the emission dispersion among the buildings. Yeah, urban physics, as Professor Kulkash mentioned, we have urban physics problem, and as you can see, climate, energy, health, security, transport, and aging problems are directly related to the interdisciplinary studies. For example, if you look at the thermal environment, there are one presentation yesterday about the thermal environment, and also pollutant dispersion, which I'm going to talk about today, and pedestrian level wind. We never look at it. The most famous example of this phenomena is the Canyon Mall near us. Natural ventilation and also has a great importance when you think about the HVAC systems. And also, as you can see, there are many interdisciplinary studies that we have to think about when planning urban. Okay, especially in urban areas, where the emissions from sources higher, the effect of an additional emission source. I mean, a three-generation system or cogeneration system which will be located in urban area. Nearby tall buildings, in here, this is the most important thing, because tall buildings have different characteristics than other buildings. On the emission distribution poses a major health threat to those living in that area. So we have to think about it. For example, a study by Iodis et al. Was performed in Italy, and in the study, NOx concentration and PM10 concentration were considered. As you can see, the location of stack is here, and as a result, 2% increment for the emissions of NOx and PM10. All the factors determining the location of the electricity production facilities in urban and regional planning is the wind direction. Prevailing wind direction has great effect. The height of the stack is also great importance. Emission sources close to tall buildings should also be addressed in terms of airflow and pressures. It's important, pressures around the buildings. Inappropriate layouts may trap the emissions among the buildings and threaten the health of the residents. And determination of concentration of contaminants between buildings is important in the buildings close to emission sources, especially in buildings that are ventilated with natural or mechanical ventilation systems. If we look at the natural ventilation and mechanical ventilation systems, if in the first day, presenter talked about it, if outside emission concentration has to be, emission concentration has to be taken into account. And if it is more polluted, there is no need to open your window or naturally ventilate the building. And also in the mechanical ventilation, the location of the fresh air intakes has crucial importance. There are many models that are used in modeling, such as Gaussian models, Ashray and customized solver are used, these models. Lagrangian and Euler models, which are CFD computational fluid dynamics models, analytical calculation methods, and wind tunnel test or models as an experimental study. CFD studies includes comparison of turbulence models, the effect of mesh structure on the results, and modeling of atmospheric boundary layer. If you want to model a urban, you have to consider the atmospheric boundary layer and effect of surface roughness. I'm not going to talk about it, but generally standard K epsilon model is preferred in the modeling, but direct numerical simulation or large eddy simulation has more accurate results, but their CPU times are 25 times higher than standard Capstone or Reynolds average Navier-Stokes models. And the mesh type has great importance in the modeling, because if you use a tetrahedral mesh structure, you are going to have a relative error 15 to 30%. And on the other hand, if you use hexahedral mesh structure, the relative error will be 5 to 10%. And as you can see in the modeling, CPU cost, resolution, and accuracy should be taken into account. In our case, this is the hospital building, a health campus with 17 buildings. That building is in here under construction, and other have 17 buildings. Inpatient bed availability for this building is 445, and plus 437 after the construction finished. And this yellow arrow is the prevailing wind direction that are used in the numerical simulations. Two cases we have. In case 1, or in case A, the three-generation system is located close to high-rise building by maintaining existing buildings on the island. For case B, the buildings that are not to be used after construction of the other high-rise hospital building are pulled down, and the energy island is located further away from new hospital building. Fresh air intake apertures of the air handling units are placed plus 20-meter height of the building on the leeward side. Here you can see for the geometries that are generated for numerical simulation. This is for case A, and this is for case B. As you can see, we have energy island here near the tall building, and all other buildings are don't pull down. And in here, these buildings are not going to be used. We should pull down them, and energy island can be located in that area that should be further away from new hospital building. Okay, in the modeling, as I said in the beginning of my presentation, atmospheric boundary layer and horseshoe effect and pressure on that side should be taken into account, as you will see from the results. An atmospheric boundary layer modeling need to be a surface roughness factor, and the velocity profile, turbulence, and kinetic energy dissipation has to be in logarithmic scale as shown in here. And the dimension of the enclosure has great importance in our solutions because of artificial acceleration of the air inside the enclosure. The blockage ratio, wind tunnel experts can know the blockage ratio, same is used in numerical simulations. And after these calculations, the dimension of enclosure is found. And this is another study from Blocken. And as you can see, please look at the wind direction and where the emissions goes. Tall building and emission source. Okay, if you look at, this is the roughness factor, you can find it. And these are the boundary conditions for three-generation systems and emissions. And here are the results. For the height at 1.7 meters, as you can see, the carbon monoxide is trapped among the buildings. This is the breathing zone. And please remember the photograph of this experiment, and please look at here. This is the emission source, and the highest carbon monoxide concentration is found to be in here. This shows that, or this verifies that our numerical study is correct. And if you look at the NOx molar concentration, it's again trapped among the buildings. The velocity vectors and streamlines are shown. As you can see, there are a huge number of vortices generated due to tall building, and this streamline is for the height of 20 meters, which fresh air intakes for the tall building is located. And as you can see, we have a vortex again in here where fresh air intakes are located. For case B, as you can see, we don't have any building anymore. We pulled down all of them and we locate the energy island further away from new building. And this is the results of NOx molar concentration, the velocity vectors and streamlines. And I have to finish my presentation. If I say the conclusions, accumulation of emissions among the buildings on breathing zone, or fresh air intake, which mechanical ventilation, on the leeward wall of the tall building poses a health risk for the staff and inpatients. Although the use of such system in urban areas has many positive results in terms of energy efficiency, the regulation of the dispersion of emissions among the buildings and the identification of critical areas must be regulated. Rather than considering a discrete system for each building, district heating and cooling of regions with correct urban region planning will be both more energy efficient and healthier for the residents. Thank you very much for listening to me.
Thank you for this valuable presentation. The building aerodynamics is one of the hardest problems of building physics.
Yeah.
However, we have some tools to have nice, colorful pictures, but they may not represent the real life, so it is really very hard problem.
Yeah.
As we have experience in canyon building, they are trying to prevent the wind. They put some barriers, but the wind is changing the way, so it's not so easy to prevent like that. So thanks a lot. If we have questions, maybe we can take one question, please. Then after that, we will have a certificate ceremony.
I asked two questions. One is your formulation is empiric or governing analytical formulates. And second is you test it in wind tunnels. Wind tunnels.
No experimental study, but another experimental study is shared in the slide. As you can see, the emissions goes through the mechanical ventilation system. It's verified our solution. And again, there are many convergence criteria for the building physics. The convergence criteria will decide your solution is correct or not. Then I don't need an experimental study for this case, but if I satisfy the convergence criteria for other numerical parts, then it's okay. But I didn't understand your first question. I didn't understand the first question.
Your equation is empiric or fluent?
No, I used fluent, ANSYS fluent, yeah, in the simulations.
Okay, thank you very much. I would like to thank all of the speakers and to the audience. Now we will have a short ceremony for the certificates. And please don't forget to fill out the questionnaire through the link on your mobile.
Sağ olun, sizinki de. Oh,
Thank you, Mr. Chairman, for the introduction. First of all, I would like to thank TMD. It's for me a pleasure and an honor to be here in this very important symposium. So I was asked to talk about the relationship between theory and practice. And so I decided to structure my presentation in two parts. So in first part, really, I will show one case study where we'll have the differences between theory and practice. And in the second part, I will give an example how to put theory in practice. So this is the outline of my presentation. I will start with something about the methods, and I will have really, I removed one of the case studies because I was told that I should use less time than I supposed in the beginning. So I had two case studies. I will use only one, and I will then pass to the indoor environmental quality monitoring tools. And the methods I will use will be based on the building analysis, on the detailed monitoring of energy consumption and indoor environmental quality, and also on thermal simulation. In our case, we use it, the design builder, for the thermal simulation. During our studies, we also conducted some subjective questionnaires, but I will not go deep in this topic on account of time limitation. So this is my first case study. It's an ICT building, a building belonging to an ICT company in Lisbon. So this study was conducted in the framework of a project which is called SUCity, Sustainable City. And this project is carried out in a program we have, it's MIT Portugal, so it's a collaboration with MIT from different universities in Portugal. In this project, my university, in this part related with buildings, because there were different work packages. There is, for instance, one work package about mobility, another one about, let us say, data circulation and so on, and another one about the use of data. In this work package about buildings, we were responsible for, let us say, the non-residential buildings. So we were analyzing two office buildings. So I select one of these buildings. It's a building with about 12,000 square meter and like 11 floors. So there are 2 floors for parking underground. There is the ground level, which is the building lobby, and the remaining 8 floors are offices, some of them as open space and some of them with small offices. So this is the location of the building. It's located in very close to the building Marco showed in his presentation. So the building is the one I'm putting here in red, and like 2 buildings beside, it's the let us say the shopping center Marco showed. This area is, let us say, an area with a particular case in Portugal, because it was the area used for the Expo 1998. So this was a project where, let us say, a previous industrial area in the town was requalified for this Expo, and there is a 3-generation system supplying the electricity and with a district heating and a district cooling network. So this building, in this building we have the possibility of somehow separating in an easy way what is heating, what is cooling, and what are electrical dependent consumptions. And just to give you an information, this is the typical weather conditions in Lisbon. So I'm showing what is the average of daily maximum temperatures and the average of daily minimum temperatures along the year. By the way, Portugal has one of the best climates in Europe, so I think the sum of the cooling degree days and the heating degree days is the lowest among all the European countries. And this is the information about the rainfall. And we may also say that Lisbon, it's a city, let us say, in the Atlantic coast, so it's a little bit windy. So air circulation is good, which means that the cleaning effect of the air coming from the sea is good for air quality. Anyway, of course, there are some exceedances in some days along the year. So this is the building shape, and you see on the left side our geometric model of the building to be used in our simulation. The building has, let us say, a window facade, and there are some holes in this facade, or let us say some architectural details. And of course, we had to be quite careful trying to simulate all the building construction details. So this is, for instance, what we have in these places with walls. So it's a composed wall, and we put all the characteristics of all these elements for our simulation. So I'm giving the data for the year 2015. So here we have the breakdown of the, let us say, final energy consumption in terms of the cost, in terms of the energy vectors. I may say that this building, let us say, annual consumption is a value of about 118 kilowatt hour per square meter per year, which places the building as a category B in the Portuguese system for the certification of buildings. So our work was, let us say, to make the diagnosis of the building and to propose some solutions to improve the energy efficiency. So here you have along the year the breakdown between the electrical energy, which is in green, and this is somehow constant along the year. We have the district cooling in blue and the district heating, and as you see, the cooling needs of the building are much higher than the heating needs, because of course we have the internal loads, and the climate in Lisbon is somehow moderate. And you may see that, for instance, even in winter time, there are some cooling needs because there is in the building a data center, and so the data center needs to be refrigerated along all the year. This is the breakdown of the consumptions according to the tariffs, to know how many are the peak hours, the hours out of peak, and so on. And this is data from let us say, detailed monitoring of energy consumption in the building. So we had like 1 month where we used our energy analyzers and the energy data loggers in the electrical frameworks. So we monitored all the circuits in the list I present. So what you see, the top graph is the energy consumption of the 2 air handling units of the building, and on the bottom graph is like the general electrical consumption of the building. Some more data, for instance, the data regarding elevators and the data regarding the consumption in offices. Of course, we see that we have a weak cycle. And so now I'm showing a comparison of let us say, the data from bills and the data from our simulation during 1 year. So in terms of what is the electrical consumption, you see that the differences are not so big. This is for heating, and here we have some differences, and the main reasons for these differences is, climate is not repeating every year as it is defined, let us say, in the typical weather or typical climate year, and also the setups of let us say, the air conditioning system are not always defined as what we have in the regulation. So people is somehow changing a little the temperature, and this is one of the reasons for this discrepancy. So this is a similar graph, but regarding the cooling. And finally, we have the overall consumption. So this is a comparison of, let us say, the bills and the simulation before we have tried to make some adjustments or some calibration. So in this case, it was not so bad. So we had a difference that in the end of the year it's no more than 15%. So it's we had already cases where we are in the 30% or 35% difference. So this was much less. So I think in this case it worked not bad. Okay, so this is from our point of view, the main reasons for discrepancies between the simulations and what we have in reality. It's the differences between the actual and the nominal weather conditions, the set point values that are chosen for indoor climate, the load profiles that are not necessarily what is defined in the regulation. Of course, the use of the spaces can be different from what was initially planned, and depending on that, the load will be different, and even the routines. Of course, we may have cases where the information that we have about the building is not so extensive, and we may have a bad definition of the geometry or of the construction details. Nowadays, that buildings are becoming very much insulated, as Marco was showing before. Ventilation rates are quite important. And there is let us say, a dependency of the ventilation rates from the weather conditions, and many times people don't measure the or at least if it is in a design phase, it's only a question of using what is in the regulation, and after when we construct the building, the infiltration rate or the ventilation rate may be different from what was initially planned. And finally, we have the very important human factor. So depending on how we use the building, the energy consumption may be quite different. So I think one of the main ideas from the presentations in 2 former days was that we must be quite, let us say, interested in the important KPIs, the key performance indicators. And these KPIs are, should be human-centered. So they should be related with the human perception of the indoor conditions in the buildings. So what I will show you next is, let's say, a case study about the really important KPIs. It's the case study of a building in the Netherlands. The story of this KPI, it's more or less the following. I have, let us say, some teaching tools available in the internet about the calculation of thermal comfort indices and so on. And so a consultant from the Netherlands found me and decided to contact me about the possibility of putting in practice a case study where we should analyze in detail the indoor environmental conditions in a building. Just a previous point. Okay, you know that, for instance, these PMV and PPV models and the adaptive model and so on exist since a long time, but they are not so much used, let us say, in the building management. So engineers are not installing this type of systems to pilot the control of the systems in the buildings. And one of the main reasons is the price. So if we want, for instance, to measure the predicted mean vote, and if we are going to the market to buy a system ready to do it, typically what we should pay is something about okay, the minimum is something about 4,000 euros. And when we compare that with the price of a thermostat that can cost like 20 or 30 euros, okay, we know that what will be the selection. So the idea is try to do that in a different way. Of course, we cannot have the indoor environmental quality monitoring system by 30 or 40 euros, but we can try to decrease the initial 4,000 euros price. So I was contacted by Leo, this consult from the Netherlands. Okay, there is another reason for that. It's the role of regulation. Because in the Netherlands, the building code changed, and nowadays it is mentioned that the building management systems should not be piloted based on air temperature, but on operative temperature. And so there is a need of having some way of measuring the operative temperature in a building. So the operative temperature takes into account not only the air, but also the mean radiant temperature and the velocity, the air velocity. And so this was the challenge, was try to have the data about the indoor operative, the initial challenge was try to have the data about the indoor operative temperature. So in this building, it's a building belonging to the municipality of the city of Horst in the Netherlands. And this building was retrofitted, and the idea was to install a system allowing us to evaluate both indoor environmental quality in all the vectors, so in terms of the thermal environment, the indoor air quality, the noise and the lighting, and also to have data about outdoor conditions. So two systems were installed, one to, let us say, two sets of sensors, one set to measure the conditions inside and another set to measure the conditions outside. So this is the concept. So in the left side, you see we have the two sets of sensors. Each set of sensor is connected to let us say a mini PC. And these mini PCs are connected to the electrical network, and we are communicating the data through the electrical network of the building. In one case, we have a wireless connection, but mostly it's done like that. The concept was the following. So the idea was to use only sensors with a USB digital output. In that case, we can use USB expanders as the data acquisition devices. So to put this working, we wrote two codes. So one code which is a data acquisition tool. So it collects the information from all the sensors. Okay, we defined a sampling time of 5 minutes. And so each 5 minutes, all the data is registered, and we have files, one file per day for each system. And so the files are stored, and stored with the name of the day. And there is a second piece of software, we call it the Discoverer, and this piece of software allows us to, let us say, to check what is going on in the building and to analyze the data and to present it. So it's a multiple window software. So we have the dashboard, a data streamer, two windows, one to see the graphs of the indoor variables, another one to see the graphs of the outdoor. There is another window showing information about the temperature of the walls, and final one window where we show the images of analyzing the building according to the adaptive model. Okay, so this is the dashboard. It's divided in parts. So in the top we have data about temperatures. After we have pressure and humidity. The third row is about the thermal comfort. So we display PMV, PPV, and let us say some indices related to local discomfort. Okay, the fourth row is about indoor air quality, and in the bottom we have the sound level, the lighting, something about air movement, and finally in the bottom in the right it's like the outdoor conditions, so regarding wind, solar radiation, and so on. Okay, now I will show a small, a video It's like visiting the system using a TeamViewer. So I've done it in my at home in my office through TeamViewer. First I saw the dashboard. This is the data streamer. So I choose one day and I may travel along the day, okay, from 0 to 24 hours, and doing that for, let us say, both the indoor and the outdoor variables. Okay, next I will move to the graphs. So I have available all the variables in the list, and I may change, I define, let us say, the starting day, the number of days, and I may change seeing all the variables, let us say, indoor temperature, PMV, PPV, wind chill index, the variables related, for instance, with indoor air quality. Now we are seeing noise, also with lighting and so on. So it's and once we have seen it, we can produce files with the tables of data. And this is something similar for the outdoor. So what we see now is the evolution of air, temperature, next humidity. Okay, there was one sensor not working at that time. It was the sensors for wind. This is like PM values for PM10, PM 2.5 and PM1. And this is solar radiation, for instance. Next, we have 3 infrared sensors. There is a matrix with 16 sensing points, 4 by 4, and we point it to a wall, and we will get the temperature distribution in the wall. So we have the temperature distribution in the ceiling, in the floor, and in the facade. And it is possible after to, okay, I select one day, and I may travel along the day and see in each hour what was the situation. The idea is that this will be used to control, let us say, radiant cooling or heating system. And this is the adaptive model. So we have the indoor operative temperature as a function of the running mean outdoor temperature. Of course, this area, it's according to the Dutch law. So we have the comfort area, and the red light is the optimal situation. So we have 2 steps. One is, let us say, the upper step in the red is the summer situation, and the other step is the winter, and in between we have, let us say, the mid-seasons. So you see we have 1 point per day, and of course in this moment I'm like reading all the files for all the days and creating the data to display. And of course if I select, I have the possibility of exporting the data in the graph to a table. Okay, so now I'm just showing you a different period. I think we can move to the... So this is like slides of what I showed, because I was not sure that it would work, so I decided to have, let us say, some slides as a safe. Here just, okay, you see the slide for all the winter season, so it's since the first day of December 2017 during 115 days. And for instance, this slide is for the summer season last year, so it's from the beginning of June and during 3 months. of course, you see that the set point temperature of the building was not exactly the, let us say, what is defined on the Dutch regulation. This is something that is, if we have a system, typically we have we overreact. So instead of having the building in 23, the building manager put it into 22. So it's, when there is a system, people like to show that the system is there. Okay, and this is another system. It's our last toy. So in that case, we have a small data logger to evaluate indoor climate. So this is this device you see here, this round device. It has the possibility of measuring air temperature, humidity, CO2, illuminance, noise, and atmospheric pressure. And so I put it together with a globe thermometer and with an anemometer. And so we have the possibility of measuring in real time the thermal comfort indices, and even of displaying the building classification. So we can see in the, let us say, a given moment, what is the category of the building environment according to ISO 7730. And we also show in this graph here the breakdown of the thermal fluxes of the human body. And for instance, as you see, this was a measurement in my home, and in a normal situation. And as you see, radiation is the losses by radiation are the most important. So in case we want to have let us say, a good control of the environment, we should measure the mean radiant temperature. It's, okay, I have a small video. In this video, I was, of course, not changing the conditions, because we cannot change it so fast. What I was changing was the, let us say, the parameters related to the person. So I was decreasing, first I was decreasing the metabolic rate. I think it's about to come. Okay, I will put the graphs, and so I started with the, let us say, normal winter conditions. So for a sedentary people, so it's a person with a 1.2 metabolic rate, and I think 1.0 closing. And I decreased first the metabolic rate. So imagine that you are in your room, and it happens very much, you start sleeping. And typically when you wake up, you feel cold, you feel discomfortable. So that's what happened here. So the conditions moved, let us say, from A or B to D, to discomfortable, because the activity metabolic rate decreased. And so I've done something similar, for instance, with the closing values. This is also a way of showing that, for instance, this classification is very much dependent on, let us say, the human parameters. And if there is a change in the human parameters, the building should have the possibility of adapting to this change. Okay, and I think that now it's just showing that the system has the possibility of, let us say, saving all the data. Of course, it's possible to select what is the variable to see on the graphs. So in the end, we may save CSV files with all the 15 parameters that are in this list. Okay, and I think that it's all. I'm even a bit in advance, so thank you very much for your attention, and I hope that Google was, let us say, good enough to make a good translation from English to Turkish. Thank you very much for your attention.
Thank you, Manuel, for your interesting presentation. There is time for a couple of questions. Yes, please, Divyo.
Yes, for Manuel, I have some questions. The first is very easy, but what's the reason to have, in the first movie you show, to have adaptive comfort index if the building is heated and cooled? Because can be a wrong, let's say, sign you go to the user, because you cannot apply adaptive control in controlled temperature building.
No, you even have, let us say, for instance, in the European standard, you have adaptive model, let us say, comfort area for free-running buildings and for mechanical ventilated buildings where you may have a HVAC system. So,
yeah, but you know that not always the standard are saying the truth, because the data are coming from the other side, not mechanical ventilated building. The data were provided to build up the correlation.
Now, this data is from, it's not, let us say, the same as the European standard, it's from the Dutch standard. And, okay.
We assume there is background behind.
Let me just give you my opinion about the adaptive model. Adaptive model is not different, for instance, from PMV. When you are using adaptive model, it's, let us say, it's like using PMV in a situation where you don't take into account humidity because you consider that humidity is not so important if you are, let us say, in the comfort zone and for a person with a sedentary activity. Humidity becomes important when you need sweating. And so if you are in a comfortable environment with a sedentary activity level, humidity is not so important. So this is one reason. And the other restriction in the adaptive model regarding to PMV is that you are considering that the metabolic rate is 1.2. Besides that, it's the same thing.
Well, we will discuss later, I don't believe so, because the statistical basis, which is not the same way being derived. Then the answer of the people has been made different.
The answer to your question is because it's to be used in the Netherlands, and in the Netherlands, you want to have it in, let us say, want to have this kind of evaluation. So it should be according to the standard.
I accept this as an answer, it's not a scientific answer. But instead, it's much more important, the point you just touched, because you said from one side we have what we like to know from the building and what the building are just telling to us. Then you had the simulation model from one side and the measurement from the other side, and a mismatch. And you say, well, I have some possible cause, but you didn't say anything about how I can reduce this possible cause of discrepancies.
Sorry, I have to interrupt
Just
here.
finish.
This is a very interesting discussion, but the time is running fast, so I invite you to discuss a little bit deeper.
We will meet in the next, we will be together, well, let us say, many times in the coming days, so we will have time to discuss.
Indeed, it's a very important topic. From Politehnica University of Timișoara, and is also president of the Romanian Association of Building Services Engineering, and he will give a talk on special engineering technology from the concept to realization and delivery. Please, Johan, the floor is yours.
Thank you, Chairman. Please let me come near to you because my eyes don't see very good screen. Anyway, I am ready to present you a work which could be considered like good practice and that it's happened in Brussels, in Anderlecht. The name of the school is called the Treffler, which means school clovers. And I will present what means exemplary building in the concept of Brussels local local investments, let's say, and in fact, what we can, we have the actors here, the artists who are the architects design atelier, also Polytech engineering, which are the design office for the special techniques, and BPC Brabant, there is the general contractor, and my company was the general contractor for building services. That means all building services was done in this school. First of all, what is an exemplary building? An exemplary building is a building that has remarkable solution to a series of criteria regarding sustainable buildings. And this in a larger sense than just energy-related question. Thus, an exemplary building is made to be more energy efficient. That means we keep the passive standard, present the lowest environment impact in the wide sense of the term, ensure an exemplary comfort, visual, thermic, acoustic, ensure a good water and waste management, encourage biodiversity on the site, have a great architectural quality, and use reproducible and profitable solution. If we think it's more close than eco-design. Some specific value for this exemplary building, global values, it's 0.18 watt per square meter Kelvin, double flux ventilation, inside from each classroom, Canadian well, cogeneration, 6 kilowatt electrical and 11.7 kilowatt for domestic hot water, sun protection, free cooling, night cooling, bicycle parking, green roof and facade gardens, fountains, green semi-intensive roof, rainwater tank, 40 cubic meters, retention basin, building site waste sorting, wall ceiling with acoustic insulation. The school, you see, has a very nice architecture. It's a nursery and primary school of 750 pupils. The local authority from Anderlecht area, Brussels, and the surface it's 9,100 square meters. The architecture is inspired by Professor Mitsuru Senda, a Japanese professor, and you see the concept is to have a facade in the circular shape and not rectangular, that reduce, in fact, the facade with 20%, and on the other side, encourage the pupils to run in the school. That means the circular form inspire and encourage the children to exercise more. Inspired on a clover, the four circle inspired a clover. Each circle has its own age section and on playing ground, and the circle is interconnected between them. let's discuss about the concept from the urbanism point of view, the mobility and urban planning layout, the sustainable city it's used like concept, urban zoning area, demographic evolution, large growth of population of municipality of Anderlecht, proximity of public transport, subway, buses, cars sharing, biking and walking area encouraged. The location taking also in account the biodiversity, it's available for the neighborhood, opportunity for social interaction, green roof and green facade, vegetable gardens surrounding the school, both for educational and also for the neighbors. That from education point of view, encourage the children to use the garden and to know what is happening in the garden. From architectural point of view, the basement is, in the basement we have the technical floor, the kitchen area, healthy for awareness and school ground vegetables. The ground floor, it's for entity in a circular shape, how you see. Three entity of primary and nursery school, playground in every circle, and at the intersection of the four entities, we have a dining room, in two zones that can be joined for bigger events if it's necessary. The upper level, we have running tracks interconnected between each circle and connected with the ground floor playground by stairs and slides. How we see the roof are green. In fact, we have 4 circles for the school, and in this zone is the gym hall also. Regarding the relation with the techniques, it was calculated 9 kilowatt-hour per square meter per year for the school and 7 kilowatt-hour per square meters per year for the gym. We can see we are nearly close for the nearly zero energy building. In fact, after we finished the school, we measured, and we have 11 kilowatt-hour per square meters per year for the school and 9 kilowatt-hour per square meter per year for the gym. Architecture and installation, the daylights. It's an important contribution of daylights, independent from the artificial lighting during the school hour. The daylight factor in the classroom is more than 5%. The daylight autonomy in the classroom is off 80%. High performance thermic isolation. Floor isolation, 130 expanded clay granule with the U value at 0.78 watt per square meter per Kelvin. Wall insulation, 36 centimeter glass wool. Roof isolation, 30 centimeter of polyurethane, and carpentry isolation with UF 0.8 and UG 0.6 triple glazing. We have here a section in the school, and we can see the roof, which is a green roof, also the isolation 1.3 meter in the ground, and we can see the triple glazing and how the daylighting it's used. Each classroom has air handling units for the ventilations, and it's on the hall and in the fourth ceiling. airtightness, it's a very important issue. All constructive nodes has been detailed and simulated with the help of program to ensure a perfect continuity of the insulation and of the airtightness barrier. Regarding the heating in the school, we have condensing boiler, heating plant with 2 condensing boiler. The heating is independent of ventilation to ensure an optimal thermic comfort of the internal and external take in the classroom. Ventilation with free cooling and night cooling in order to ensure the thermic comfort in summer validated by the dynamic simulation. Heating with radiators in the classrooms and other rooms, which has a rapid reaction of the system. Floor heating in the hall. The gym heating plant, it's with the condensing boiler and cogeneration. And the ventilation system, it's and the heating is the ventilation system and radiant panels and locker room with radiators. From the electrical point of view, in the school we have high-performance lab with lamps with electronic ballast, artificial lighting management to the light intensity of movement sensor. In the gym we have 2 levels of lighting for the training and for the competition. And of course, the building management system, an important issue, an important realization for this building. The sanitation facility in the school, the production of domestic hot water is with a condensation gas boiler. And in the gym, we have cogeneration for production of domestic hot water, simultaneous production of heating and electricity, equivalent to 25% of the hot water needs of the project, electric-powered 6 kilowatts storage reserve in the tank from 1,000 liters. The monitoring, it's very important because we can verify that the functioning of the building remains compliant to the initial concept. The monitoring of the building installation is done by electric meters for each electric panel, electric meters for each HVAC device, methods with the heating integration for each heating circuit and cogeneration, impulsion methods to measure the gas and water consumption, and consumption panel of the entire site of the properties. Some picture, how you see on the whole we have floor heating and air handling units for each classroom. More detail about the ventilation concept. In the classroom we have air handling units with a double flux system with high efficiency for the heat recovery. Automation of the airflow with the help of temperature and CO2 sensor. Ventilation to free cooling and night cooling for thermic comfort during summer. The quality of the interior climate comfort is paramount for the health and performance of the pupils and children. For each equipment, for each classroom, regarding the air handling units, we had first of all one classroom which was measured by independent organisms, and they showed that all the equipment is according with the design, and we measured the airflow for each classroom, the loss pressure, also the efficiency of heat recovery in three hypostases in the condition, nominal condition, that means -8 degree outside and 20 inside. In the condition of EN3 or 0 with 5 degree outside and 25 inside, and the total efficiency taking in account electric engine of the fan. An important parameter is the specific fan power. it was imposed to be in the second level of that. That means less than 7,500 watt per cubic meter per second. And for each equipment we measure that, and of course the sound pressure for each equipment, and in the classroom it was imposed to have 40, less than 40 decibel, and each equipment was had sound dampers to avoid this task. How you see, we measure inside the in the ducts, we measure the airflow and also the speed of air. Some picture and of course some words about the building management system. It's imposed by the BATEX, which is an exemplary building, and we have the time schedule from each days of the school. We have here the parameters of each monitoring systems from electric energy, from the school for the gym hall, water from the school, from the gym hall, gas also for the school and for the gym hall. The screen which the heating system, heating plant for the school, the condensing boiler, the systems and the distributor and the collector for the system, the domestic hot water in the condensing boiler, one school, and from the hall we have floor heating and also free cooling systems. From each class, we monitoring the airflow, the temperature, the concentration of CO2, and also the level of lighting for the stores. The heating plant for the gym with the cogeneration system and the condensing boiler, the distribution. Also the production of domestic hot water, the air handling units for the gym hall, and we have a picture in the natural area here from September 2016. The school it's in function. Here are the clovers which is in the main hall of the school. I want to finish my presentation inviting once again you to Clima 2019 next year in Bucharest, Romania. Here are the personal contact and also the contact on the site. And I want to thank once again Daikin, who is the main sponsor, one of the diamond sponsor of Clima 2019. I want to thank to Intech Belgium, is the second diamond sponsor for us, which is very important. And I want to thank also to our host TTMD Society for hospitality, and we await you in Bucharest to show that we can provide the same hospitality. And of course, everybody is invited to attend Clima 2019. Thank you very much. Question?
Thank you very much, Johan. There's time for some short question. I have one.
Yes, please.
You showed that you are monitoring. Have you compared a full year of energy demand with measured and monitored?
Yes. It's how I said before. From the passive value, we were in the 11 kilowatt hour per square meter per year for school, and 9 kilowatt hour per square meter per year for the gym. It's mandatory to have this screen with each consume of metering, and there's a screen in the main hall, and that can be see how it's working and how we achieve the...
If I remember well, compared to the first value you show, it's a little bit higher, isn't it? It was 9 and 7.
Which one?
The simulated energy demand.
9 for the school and 7 for the gym.
And you get 11?
11 and 9, yes. But we are less than 15 kilowatt hour per square meters, which is the passive house.
No, but my question was more, let's say, theoretical, and in a way it's also a question to Manuel about what is shown. I'm every time puzzled because we say that performance gap has many reasons. And it's basically the fact that we don't know exactly which are the boundary condition, human factor, and so on. But what I'm wondering is that if the error is about ignorance, it should be distributed like Gaussian, like a normal. So you should find sometimes higher value, sometimes lower value. What happens is that every time you simulate and then you measure higher value. So it seems there's a bias besides ignorance. A comment from both of you.
I want to say another thing because yesterday it was spoke that it's most important to have the databases and not the energy is the problem now, to how we use the databases, what it's happened. They ask us to each 15 minutes to have data from more than 30 parameters, and nobody looks 3 months of the databases. After 3 months the system was blocked. Effectively it was blocked, and we consider that it's not necessary to have every 15 minutes to evaluate the energy efficiency of the building and consumption. And here it's also regarding the commissioning, what we spoke yesterday, it's one point which can be detailed. That's it, I think. Okay, thank you.
You have a comment? You have a comment, Manuel?
Good afternoon, everyone. My name is Anıl Başaran. I am a PhD student in Manisa Celal Bayar University, Department of Mechanical Engineering. I have divided my presentation into 3 parts. Firstly, I will start with a brief introduction. After that, I am going to talk about numerical simulation. In part 3, I will try to explain obtained results and outline this study. Advantages of mini-channel heat exchangers over the traditional heat exchangers can be listed as compactness, enhanced heat flux, lightweight, lower refrigerant charge, and higher mechanical strength. And due to this advantage, mini-channel condensers are increasingly employed in automobile, air conditioning, heat pump, and electronic cooling applications. In the condenser designs, fins are placed in the air side of the condenser to increase overall heat transfer coefficient. And also, in the air side thermal resistance generally accounts for 90% of the total thermal resistance of a finned heat exchangers. This value is quite high, and therefore the fin arrangements becomes one of the design parameters which can influence on mini-channel heat condenser performance. On the other hand, simulation tools provides accurately prediction of the condenser performance to designer and researcher while reducing design and improvement cost. In these concepts, the main purpose of this study is to investigate effects of different fin geometries and air inlet velocities on heat transfer and pressure drop in mini-channel condensers. In this study, we considered 3 fin forms for a mini-channel condenser. These forms are elliptic, triangular, and square. And also, after that, we conduct a numerical simulation to examine fluid flow and heat transfer characteristic in a mini-channel condenser. Heat flux from the fins and pressure drop caused by the fin geometries have been analyzed numerically. And a mini-channel condenser, schematically shown figure 1, was handled during this study. Mini-channel condenser consists of flat multi-port mini-channels, and fins are placed between these slabs. And also, can you see in figure 2, considered fin geometries, elliptic 1, triangular and square. Figure 2 also indicate the translational periodic elements. We used the translational periodic elements to reduce the computational time and efforts. And in the figure 3, you can see in the dimensions of the fin geometries. During the analysis, the fin dimensions, the fin geometries of the dimensions of the fin geometries was fixed for the comparison. And also the air flow pass over the fin geometries was modeled with an enclosure. This enclosure is numerically investigate flow domain. In the enclosure, the length of the enclosure behind the fins was held twice as long as fin lengths in order to model the vortices that may be formed in this region. And in this simulation, the flow is modeled as a three-dimensional, laminar, and incompressible. Also, the air is assumed as ideal gas. The mass and momentum and energy conservation equation can be written as governing equations. If we talk about boundary conditions, at the air inlets, x and y component are equal to 0, and z component of air velocity is equal to W0. At the air outlet, pressure is equal to atmosphere pressure. At the tube wall, x, y, and z component of air velocity are equal to 0, and the wall temperature is equal to 14 centigrade degree. The wall temperature was kept at 40 centigrade degree during the simulation due to the fact that the temperature does not alter during the condensation. Governing equations and boundary conditions were solved with a commercial software package ANSYS Fulian. We used academic versions of the ANSYS Fulians, and in the numerical simulation, the least square cell-based method has been used to evaluate gradients. And for the pressure interpolation, the second order scheme was used. And the momentum and energy equation were discretized using second order Altman scheme. For pressure and velocity coupling, the simple algorithm was used, and convergence criteria are 10 over minus 3 for momentum, 10 over minus 4 for momentum, 10 over minus 3 for continuity, 10 over minus 4 for momentum, and 10 over minus 6 for energy. And in this section, I want to talk about obtained results. This graph shows the variation of heat flux with different air velocity. It can be easily seen from the figure. The heat flux increase with increasing air inlet velocity for all investigate fin forms. And among the fin geometries, elliptic one shows the lowest heat flux, and triangular and square fin geometries have nearly same heat flux. And another figure represents the pressure drops in the numerically investigate flow domain. Here, heat transfer rates related with heat flux and heat transfer area. Heat transfer area of investigate fin geometries in numerical flow domain can be seen table 1. And here triangular fin forms shows the highest heat transfer rate due to its height heat flux and moderate heat transfer area. And figure 6 shows the temperature contour at 2 meters per second air inlet velocity. And here, in the triangular fin forms, there is an increment of the temperature gradient. You can see with a red color. This means that there is an enhancement of heat transfer rate in triangular fin geometries. Another figure shows the pressure drop in a numerically investigate flow domain. And pressure drop is one of the design parameters have an influence on performance of the condenser. Similarly, heat flux, pressure drop increase with increasing air inlet velocity. And among the fin geometries, square fin form give rise to lower pressure drop than the other fin geometries. And also between 2 meters per second and 4 meters per second air inlet velocity, there is a substantial increment for all investigate fin geometries. And figure 8 represents velocity streamlines at the 4 meters per second air inlet velocities. In the elliptic fin geometries, distorts the streamlines more than other fin geometries, and it causes high velocity along the fins. On the other hand, square fin forms give rise to less flow separation at the fin entries, and this situation results in less pressure drop in the square fin form. Finally, I want to finish with a summary. In the considered mini-channel condenser, the heat flux from the handled fin geometries for screened air inlet velocities were obtained in the range of 200 and 850 watt per meter square. Both the heat flux and the pressure drop increase with increasing air inlet velocities. On the other hand, increasing air inlet velocities cause fan power consumption to increase because the pressure drop increase with increasing air velocity. Both the heat flux from the fins and heat transfer rate have an influence on heat transfer rate in the mini-channel condenser. Optimal fin geometry design should be done both in terms of the heat flux and heat transfer area. These are references used in this presentation. Thanks for your listening.
Thank you, Anil, for your interesting presentation. There's time for questions, please.
Thank you very much for your presentation. Now, could you go back to the slide, please? The presentation, please. Now, I have two remarks. One is, instead of using an absolute velocity, like 0.5, changing between 0.5 and 4, why not using Reynolds number? I mean, because as you know, you could have expressed it in terms of non-dimensional parameters, which is Reynolds number here. That's my remark, but of course it can be done. The second thing is, I might have missed, but during your speech, during your presentation, I wondered whether you, the three geometries you tested, were they common in terms of hydraulic diameter?
Sorry,
I mean, did they have a common hydraulic diameter? I mean, okay?
Okay.
Or did they have a common cross-sectional area? Because I'm afraid if you have differing areas, side areas, because of friction, it's natural that you would find different results. But comparing those three tests, those three configurations, based on a common parameter, a fixed Reynolds number, and a fixed hydraulic diameter, for example, would mean a little better. That's my personal remark. Thank you.
Thank you for your comment. Firstly, this mini-channel condenser were designed for a refrigerator, an exist refrigerator. And in these refrigerators, we have only data in air velocity. We have only data in air velocity, not Reynolds numbers. So we used these air velocities, and then we calculate Reynolds numbers.
Okay, but I still insist, because for future usage, Reynolds number
yes.
would mean a lot for a future researcher.
Thank you very much
Thank
for your comment.
Thank you. Yes, please.
Okay, thank you very much for the presentation. Actually, you modeled only air side, right? The flow in mini channels are disregarded. Is it okay?
Yeah.
And I exactly agree with Professor Çakan about the non-dimensionalization of velocity. And secondly, if you model air side, how it can be possible to use laminar boundary condition for turbulence model? The velocities, I mean, or with hydraulic diameter is small enough for laminar boundary condition, which I don't believe it could be in laminar region, because it must be in the turbulence region. And in addition, you have to take into account boundary layer generation in these channels. And also you have to look at Y+ values when designing the air side of this condenser. Thank you very much.
Thank you for your question. Firstly, I said earlier, we have only air velocity values for the exist refrigerator. So we calculate and Reynolds numbers, and these Reynolds numbers and air properties and hydraulic diameter between the fins in the range of the laminar flow in the Reynolds numbers. So the flow is modeled as a laminar flow. This is only air side modeling, and we have not conducted yet inside the refrigerant site. I said earlier, we have a refrigerator and we have some data in these refrigerants, and we try to design a mini-channel condenser in the data that have us.
My name is Tolga Güler. I'm a physics engineer and I have been working in HVAC industry for 6 years. Okay. Yeah. Ladies and gentlemen, good afternoon. Thanks for being here until this time. My name is Tolga Güler. I'm a physics engineer and I have been working in HVAC industry for 6 years. My study covers comparison of 3 different coil models in CFD simulation, considering their positive and negative aspects. And this is the content of my presentation. You are seeing here motivation, closer look at coil, different modeling approaches, boundary conditions, and details of the models, and simulation results and conclusion. Motivation. Coils are essential equipments in the HVAC industry. For this reason, they are included in many analyses. And CFD analyses help us to investigate the pressure losses and the other airflow characteristics of our design, HVAC design. And during design process, we make several changes on the unit design, and we apply these changes to our unit design. And at this point, CFD analysis provides us economical solutions rather than the physical experiments. Sorry for this. Rather than the physical experiments. And our purpose of this study is here to reach a feasible HVAC system design verification workflow with less number of physical experiments and computational demanding to be required only at the introduction of the new design families, and simulation applicable in the industrial time frames. Our modeling approaches are, the first of is grid modeling. In the grid modeling, either a full CAD model or reverse engineered CAD model can be used in the analysis, and we have 5 cells between the neighboring fins in the grid model approach. And the second model is the gap model, and it's the same. Either we can use the original manufacturer's CAD model or the reverse engineered CAD model in the simulation. But there's a difference for cells, and there's only one row cell, gap cells, between the neighboring fins in the gap model. And the last one is the coil approximation by porous modeling. Coil geometry is non-existing here. Coil is only defined as a simple box, but its positioning is addressed in the simulation. And coil is defined as a volume resistance with a specific resistance coefficient. If we look at the coil, the close-up, we are seeing the length of the coil for 460 millimeter, 200 millimeter, and 60 millimeter. And if you look at the fin distance, it is significantly smaller than the exterior dimensions of the coil. If you look at the ratio of the length and the fin distance, it is larger than the 200, and this causes the dimensional problems in CFD simulations. This big ratio makes difficulty to create a good grid generation in CFD simulations. Please keep this picture in your mind. And this is the boundary conditions we are using in the in 3 models. Please note that all boundary conditions are same in all simulations to ensure the results while we are comparing the results. You are seeing the inlet section and outlet and symmetry and the wall boundary conditions, and the computational domain is a simple duct here, and the coil is in the middle of the computational domain. If if you look at the positive aspects of the grid resolution, we see that the high fidelity representation of the real-life applications, and you are seeing a coil surface on the picture, and the other positive aspects of the grid modeling approach, more accurate and the more realistic results we are getting. And if you look at the positive aspects again, we get a better agreement with the experimental results. And what are the negative aspects of the coil grid definition? The geometrical problems. The first problem is getting an original 2D model of a coil from the manufacturers because there is not any manufacturer in Turkey providing any 3D real model of the coil. There are only some two-dimensional models they can provide us. The second way is the creating our 3D model by reverse engineering, and we have some problems here while creating our own 3D models because reverse engineering brings some measurement and tolerancing problems with it. And the second problem is meshing problems because we have very small gaps between the coil's lamels, fins, and outside the coil we have larger cells around the coil, and we need to create a transition mesh area after and before the coil to avoiding convergence problems. And another problem is grid modeling. We need enormous computational power because of high count of grid cells and the complex geometry of the coil. And another problem is data losses for separate solutions. Imagine a handling unit. It is consisting some parts fan side box and coil side box. In this approach, engineering approach, we are dividing unit into the separate parts in an order, and we start simulation at the first part, and when we finish the first part, we are using its outlet to second one's inlet, and the third one's second one's outlet is the third one's inlet, and this transition between the parts brings the data losses. And our second model is gap model. You are seeing in the picture gap cells. If you look at the positive aspects of the gap modeling, effective resolution of flow in the spacing between fins, and you don't need to spend too much meshing efforts. A program generates gap cells automatically and detects the gap cells where must be created in the computational domain. There is only one row cells in the bit spacing instead of more than 5 or 5 or more than 5, and significantly less number of total cells in reduction. In this project, we achieved the 85% cell count reduction. And due to the reduction of the cell count, the computational times also reducing, and at this project we achieved the 50% time reduction with gap cells. If you look at the negative aspects of the gap model, we cannot solve the boundary layer problems with gap model. And we cannot solve complex spatial flow gradients such as supersonic shocks. And there are some always errors for bulk parameters, for example, pressure drops, mass flow, and total heat transfer. And the last model is we we used porous modeling. It's if you look at the porous modeling's positive aspects, significantly decreasing, we are seeing significantly decreasing number of cells we need and significantly decreasing computational resources. And according to these two number of cells and computational resources decrease, and we achieve the less calculation times, and it is much more reliable and practical to perform a whole system analysis. And you are seeing the package air handling unit in the picture, and there are two coils, two filters, and there is a heat exchanger. Also, two fans are here, and these are not statical. They are rotating in the simulation, and there is a mixture damper in the simulation here, and we can do this with post-medium definition. If you look at the negative aspects of the post-medium definition, intensity to flow field characteristics generated by coil, we are losing some details. This picture is from the gap model analysis, and we lose these details and turbulent areas in the post-medium definition. And the other problem is difficulty to obtain the accurate heat transfer data because we don't have any heat transfer surfaces. It is just described as a volume heat source in the analysis. And the most difficult problem is here, defining the porosity or the permeability or the resistivity coefficients or function or the table. It is the most difficult thing is here in the porous definition. And if you look at the overall simulation results, you are seeing the mesh count in the grid approaches, 5.78 million grids we used, and the gap model we used in 900K nearly, and the last model is the post medium. We are seeing just only 75K grid count we reach. And if you look at the pressure drops here, you are seeing the same pressure drops nearly we achieve. But if you look at the last column of the table, coil selection software, you are seeing comes from the value, and it is different, more different than other values, because this error comes from the reverse engineering issues and measurement and tolerancing mistakes while we are creating our own 3D coil model. And if you look at the temperature changes, it is close to each other, we can say, and heat flux also says the same thing as to us. And now we can look at some visual results. You are seeing the grid picture, and in order by gap model, porous medium, and the grid modeling at the end of the picture. And we are seeing the dense meshing for grid modeling, and porous medium is homogeneous meshing, and the purple one is the gap meshes created by the software. And this is the top view of the meshes we are created. And this is the velocity color contours. You are seeing the turbulent areas and effects of the tubes of the coil for both gap modeling and grid modeling, but we cannot see the turbulent areas for porous modeling. We are losing these details. Also, top velocity, we are seeing the same picture for velocity, and pressure color contours we are seeing. It is similar because we defined the porous medium as a volume resistance. You are seeing the same picture, similar pictures for 3 models. And this is the top view of the pressure. And the last one is the temperature. You are seeing geometrical effects in grid modeling and the gap modeling, but there is not any geometrical effect in pores definition. This is the top view of the temperature values you are seeing. And the conclusion. If you look at the computational cost, the porous medium is the best because it uses less computational resources and requires less time. And gap model is the second, and the grid result is the last one. And if you look at the accuracy of our simulation, porous modeling has 8% difference between the grid modeling, and gap model is 1.25 difference from the grid modeling. And if we combine this together, the best performance cost ratio for gap modeling. And I want to say something more about if we are interested in pressure drops only in our design, we can use porous definition, and if you want more details to obtain in an acceptable time, we can use gap modeling. If we have enough computational resources and enough time, if you want to see every details, we can use the grid modeling. If you want to, sorry, I want to finish I want to say some sentences about our industry. We are designing every day in different HVAC units such as fan coils, air handling units, etc. Each unit has one or more coils, and we are selecting these coils from selection softwares. And the selection softwares gives us some capacity and thermal property of the coil under laminar flow. And we have what we have in the real life, the picture is different here. And CFD simulations tells about more capacity losses, pressure losses, and other airflow characteristics of our design. Thank you.
Thank you, Dorga, very much. Thank you for a nice presentation. Just a second, maybe there are some questions. Other questions? Okay, now everyone is looking forward to the coffee break. Okay, so thank you again.